We are sitting on a rock, zooming through space. Earth orbits the Sun, and the Sun orbits the galactic center. But the entire Milky Way Galaxy is also hurtling through the universe at over 630 kilometers per second. For a long time, the standard cosmological explanation for this massive movement was simple attraction. The assumption was that the combined gravity from visible, massive superclusters of galaxies ahead of us was hauling our local group forward. This chart shows the mathematical problem. On one side, we have the immense gravitational force required to drag the Milky Way at 631 kilometers per second. On the other side, the actual observed mass of nearby superclusters falls wildly short of producing the necessary pull. The math did not balance until astrophysicists looked in the exact opposite direction. They hypothesized we aren't just being dragged forward by visible mass, our trajectory is also violently propelled from behind by a massive unseen force. To accurately navigate the cosmos, we have to look beyond the glowing stars and galaxies. We must map extreme physical forces that exert massive influence without leaving a visible footprint. That force pulling us forward is an area called the Shapley attractor. It is an incredibly dense concentration of thousands of galaxies, roughly 650 million light-years away, acting as a massive cosmic magnet for our local group. Directly opposite the Shapley attractor sits its geometric counterpart, a vast empty region of space, almost entirely devoid of galaxies. This is the dipole repeller. This is a map of the gravitational potential surfaces enclosing these two regions. The green area is the Shapley attractor, pulling matter in. The yellow area is the dipole repeller. Because this yellow void lacks mass, it creates a region of extremely low gravitational density. The surrounding, denser regions naturally flow away from this empty pocket toward the heavier mass, resulting in a physical push. By analyzing the red shift, how light stretches as objects move away from us, astronomers measured the velocities of thousands of nearby galaxies. You can see the result in these streamlines flowing directly out of the yellow repeller void and sweeping toward the green attractor basin. Notice the red knots and gray filaments suspended here. This is the cosmic V-web. The physical distribution of these galaxy clusters is completely dictated by the interplay of these two opposing, invisible forces. But macroscopic flow is only half the equation. If we zoom in from these giant superclusters down into a single planetary orbit, the nature of the invisible threats changes drastically. Charting the gravitational movement of entire galaxies is useless if our physical technology shatters the moment it encounters the intense, localized energy fields surrounding the planets themselves. The most hostile local environment in our solar system is Jupiter's magnetic field. It is a mammoth structure, swelling to an average width of 20 million kilometers. That is 150 times wider than the gas giant itself. This cross-section shows the mechanics of that threat. Jupiter's magnetosphere acts as a natural particle accelerator. It traps the solar wind and captures charged ions violently ejected by its volcanic moon, Io. The field then whips these particles up to relativistic speeds. The resulting radiation belts are roughly 100,000 times more intense than Earth's Van Allen belts. A human exposed to this environment would receive a lethal dose in a matter of hours. For a robotic probe, the environment is just as deadly. When a single charged particle impacts a microchip at these speeds, it triggers what engineers call a single event upset. This microscopic collision creates a brief electrical discharge that can flip computer memory bits, induce random glitches, or cause catastrophic short circuits inside a spacecraft's brain. To survive this, missions like the Jupiter Icy Moons Explorer, or JUICE, rely on extreme material engineering. The probe's most sensitive electronics are locked inside twin vaults built from carbon fiber and heavily reinforced with lead. Individual components receive additional spot shielding using dense metals like tantalum. Engineers design modern space probes as heavily fortified microenvironments, built to physically absorb and deflect highly localized invisible radiation. You cannot launch a billion-dollar probe toward Jupiter and simply hope the shielding holds. The hardware has to be physically tested against the radiation before it ever leaves the ground. To replicate Jupiter's lethal environment on Earth, engineers borrow medical particle accelerators, normally used for cancer treatment. They place the computer chips directly in the path of the beam and use cobalt-60 isotopes to intentionally bombard the components with gamma rays. By meticulously recording exactly how much radiation it takes to cause a short circuit, engineers feed the failure data into a software system called SPENVIS. This generates a predictive model, telling mission control precisely when and how a specific component will die in space. We map the macro scale of the universe using supercomputers to track the invisible gravitational push of the dipole repeller. We map the micro scale by using particle accelerators to track the invisible threshold of radiation death inside a microchip. Whether we are calculating the flow of entire galaxies or reinforcing a single memory board with tantalum, our continued exploration of the cosmos relies on a single capability. We have to map, model, and ultimately out